Okay guys, I put together one more lecture clip. This is stuff that normally we would have gone over in class during student presentations, but since we didn't do presentations in this online version, I'm going over these real quick with you. Most of these can be found in chapter 16 in your text, all right, or in the glossary of your book. So let's run down through a few basic definitions. Evidence of disease could take the form of signs, which are objective and measurable indications of a disease or infection. We're talking maybe blood pressure or temperature or bruising that is obvious to the naked eye, things that your medical professional can actually see, right, or measure. Symptoms would be a more subjective experience of disease or infection that's felt by the patient. So maybe, for example, they feel tired all the time. There's a malaise, something like that might be something that's a symptom. A syndrome would be a combination of all these signs and symptoms that are usually characteristic of one particular disease. And a lot of syndromes are named using different prefixes like you see here and suffixes also like you see here. And these are some great examples over on the right side, right? Cytopenia, so cyto, something to do with cells, and this penia part is usually a lower amount of whatever it is you put in front of it. So in this case, lower amount of red blood cells. Hepatitis, right? So the first part is for liver, the second part for inflammation. You get the idea. All right, now where are these disease-causing agents coming from, whether it be viral, bacterial, or other? One thing we can talk about is a reservoir, a living or non-living site in which a pathogenic organism can survive or multiply. Now, this, with all the news lately, the coronavirus crops in here. We can talk about bats, right? Bats are thought to have been a natural reservoir for coronavirus. So this would be obviously a living host where the virus resided. And of course, for a virus, it makes sense that a virus would need a living reservoir because they need to hijack cells in order to survive. Carriers, on the other hand, are individuals that are capable of transmitting a pathogen without displaying the symptoms. Okay, so an example might be a passive carrier, someone who's not even unaffected. So here we're talking, could even happen in the hospital, right? If you don't take proper precautions and you go into one patient's room where they have some kind of disease and you don't change your gloves or take your gloves off before going to the next patient's room, then you could carry it that way. You would be a passive carrier, not infected, and yet you brought that pathogen from one person to another. You could be an active carrier where the person is actually infected, okay? And they can carry it around that way. Or you can also be an asymptomatic carrier. So you could actually have been infected, but you're not showing symptoms yet. So you don't even know that you have it, and then you go on and pass it to someone else. And of course, this is again something with coronavirus that we're worried about. There are people that are asymptomatic that are capable of passing the disease on to someone else. And if that someone else it has greater propensity to succumb to that virus, then it's bad news, right? For that person you pass it to, even though you yourself may be asymptomatic or have very mild symptoms. All right, transmissibility. How transmissible, right, would a pathogen be? If there is a pathogen that is able to be transmitted directly or indirectly from one person to another, we say it's communicable disease, okay? And obviously, coronavirus is one of those. You can talk about maybe chickenpox, right, or the cold. Any of these would be communicable diseases. But then if you say that it's at a high level within this category, we would say it's a contagious disease. It's very easily spread from person to person. Now, this is where in your project they're talking about this R naught figure, this number that you can come up with, which is basically R naught, the 0 down here in the subscript, which the definition is it would be a reproduction rate. So R naught, if you were to pass a disease from from yourself to one other person, and then that one other person then passes to one other person, that would be an R naught of 1, right? We'd have a pretty steady transmission within a population. It's when that R naught is higher than 1 that we start running into more and more problems. So to give you an example, the flu is an R naught of 1.2. So it's a little more communicable than a 1-to-1 ratio. COVID-19, the coronavirus that we're talking about, it's on the order of somewhere in the 2 to 4 range. So let's say 3. Well, if you pass from 1 to 3, and those go on to 9, and you just keep going, right? You're going to have a more exponential growth of passing that disease. Now, that doesn't mean that everybody is going to succumb to that disease and die from that disease, but there's a higher possibility that you'll spread it to someone who will. Now, measles, the R naught is something on the order of 12 to 18. Very contagious, all right, when it comes to transmissibility. This in comparison to non-communicable diseases that cannot be transmitted. So a classic example might be something like cancer, right? So a cancer is not something that we typically think of as being transmissible. What kinds of transmission can occur? Well, you could have direct contact transmission or indirect contact transmission. So direct would be person to person, okay? Examples: touching, kissing, sexual activity, even droplet spray. If you're close enough to someone, you may not be touching them, but you sneeze, you cough, and droplets get into their eyes, nose, mouth. Mucous membranes are more likely to allow that transmission to occur. This in comparison to indirect contact transmission, where we have a transfer of the infectious agent between hosts because of a fomite. A fomite is a inanimate object. So it could be a bed rail, it could be a coffee cup, it could be anything that you touch. Okay, and with coronavirus, we know for sure that there's direct contact transmission, but we're finding that indirect contact transmission is far less likely. Doesn't mean we shouldn't be careful when touching bed rails and a box brought to you in the mail. You may want to be careful and wash your hands after touching those things, but it's far less likely for that particular virus to survive on fomites. But it's very possible with viruses and bacteria that a fomite could be involved. All right, we have other kinds of transmission, including vehicle transmission. This is a transfer where there's contaminated food, water, or air. Now, I'll give you an interesting one here. We talked about droplet transmission and droplet spray, and the fact that it would be pretty much we thought about it as a direct transmission. Even though you're not touching, you're close enough and you sneeze, right? Well, actually, that is true, but some droplets can be so small that they will remain in the air for longer periods of time. And when they're in the air for longer periods of time, sometimes they'll refer to it as vehicle transmission, and it would not be considered a direct transmission at all. Okay, more of an indirect transmission in that particular case. Classic ones here would be contaminated food, right? If there's some kind of contaminated food and it's in the grocery store and you buy it, that could be your source. It's a vehicle transmission. Or water with cholera, right? Would be a good example. Vector transmission would be where the pathogen is passing, usually on another animal, typically in arthropods. We're talking insects here typically. But it can sometimes be other organisms too. You hear about turtles with salmonella, right? Or think, what else? In this case, the classic ones I think of would be Lyme disease, where the organism is passed by the tick, right? Or malaria with mosquitoes. So the vector would be that insect in those cases. All right, how do we analyze disease in a population? Well, we can talk about incidence, which is the number or proportion of new cases in a period of time. Okay, so we'd say in 2020, we have X number of cases of COVID-19, right? That would be an example of incidence. Versus prevalence would be a number or proportion of individuals with a particular illness in a given population at that time. So we're adding everybody cumulatively, right? So we might talk about, okay, in the United States alone, X number of people suffer with HIV. That would be taking everybody in the entire population and saying there's a certain percentage of those people that have the disease. Versus we might instead want to look at HIV and say some percentage of people or some number of people will contract the HIV in a year's time. So in 2020 alone, X number of people will catch the virus. All right, using incidence and prevalence, but more so incidence here, we can actually calculate an infection fatality rate. And this sometimes is called a case fatality rate because we're talking about anybody that is in fact infected. Okay, so the number of deaths among those infected would be the fatality rate. So you can just take the number of deaths and divide by the number of total cases. And remember, the number of total cases we might be talking about in one period of time could be the incidence, right? So there's a certain number of deaths per cases, and we multiply that by 100, and we get a percentage, okay? So give you an example. In the time that we've been worried about coronavirus within the last few months, the infection fatality rate has gone up. We have seen up till April 3.2% infection fatality rate. We now think that those rates are we see that those rates are going up as the curve goes up, right? As more and more people get infected, we see that there are in fact more people dying from the disease. But we need to keep in mind that this is very hard to measure because the number of total cases is not well known. We need to do more tests to determine how many people are actually infected, how many cases are there really, okay? People are asymptomatic, so they don't know they have it. There are not enough tests out there to be testing enough people to know how many people actually have it, right? So these would be good examples of reasons why it's really hard to measure this and know if we have an accurate number. And this is where the United States has been criticized to a great extent because we haven't really been keeping up with the testing that we needed to do to be more fully informed on these things. Okay, mortality rate would be the number of deaths from a disease. So again, deaths in the numerator, okay? But in the total population, we're not saying the number of deaths in the people that catch it. We're saying the number of deaths out of the entire population, those that catch it and don't catch it, okay? And this could be, again, a percentage, so you multiply by 100, right? Deaths over the total population, and we have a certain chance of dying from a disease, right? Or you can take the number of deaths per 100,000 people, and that's a pretty common way of actually reporting it. is per 100,000 people, all right? Because if you want to compare from one country to another, for example, where is it really hitting harder? Well, it's easier to tell if you have a standard 100,000 people in the denominator of this calculation, because you can say, oh, X number of people in Italy died from it per 100,000 people. Well, we're a much bigger country, so we're going to have a greater population, right? But if you say per 100,000 people, it gives us a good way of comparing. All right, what are some of the patterns of incidence within populations? We can see an endemic disease. This would be a disease where it's constantly present, whatever that disease is. Often they're at a very low level all the time, like the common cold would be a good example. And it also is connected to a geographic location. So to say that malaria in New York State is a problem would be kind of ridiculous, right? It's not a problem. We don't have a lot of malaria here in the United States, in particular in New York State. But if we looked at malaria in maybe Nigeria, somewhere where the passing of that through a vector, through a mosquito, okay, is much more common, well, we might say that malaria is endemic in that region of the world. But if we reach those proportions here in New York State, we would say instead that it's an epidemic proportion of disease, okay? So you might have very different endemic diseases depending on where it is that you're talking geographically. Endemic diseases, these are diseases for which a larger number than expected occur in a short time frame in a particular place. So like I say, if you had the same number in a month's time of malaria cases in New York State as you do in Nigeria, they would say that's an epidemic for sure. A pandemic would be basically just an epidemic, so where the numbers are higher than typically seen, but it's a worldwide event, all right? Like the coronavirus problem we have now. All right, what about, how does the susceptibility of the members of a population affect things? So in other words, how many people are susceptible? They're not immune to the pathogen. What we talk about is something called herd immunity, okay? So within our herd, let's say our herd is all the people, right, in the United States, or just in New York State, or something like that. We have a herd of people, and herd immunity refers to a reduction in the disease prevalent within that population when only a few individuals in the population are susceptible. So in other words, a certain number of people have to be immune and resistant or not susceptible, right, to the pathogen, all right? So if they run into it, they won't get the disease. Now, this is a good number to have, right? We want to have enough people immune so that a disease doesn't spread wildfire throughout a population. And right now, we're running into that problem with coronavirus, right? It's been said that some of the people that do these calculations, that 67% of the population here in the United States needs to be resistant, have some kind of immunity to coronavirus in order for us to tide the epidemic, to keep up with the number of cases that we're dealing with. And we are not there. I think as of like March or April, we were at 20%. So we are at a third of the number of people that we need to have be immune. Now this again is a moving target. This is a hard threshold, epidemic threshold, which is the number or density of susceptible hosts that are required for an epidemic to occur, right? So when are we at the point where the threshold, the number of people that are sensitive and susceptible to disease drops below a certain point. And we have more than 67% of people that are immune. It's hard to measure because, again, in this case with coronavirus, we don't know how many people have caught the disease and recovered. We don't have a good number because of our testing of how many people are asymptomatic and have no idea they have the disease. All right. So we don't know how many people are immune because we haven't done enough of those kinds of tests. Okay. So it all kind of relates, right, to some of the stuff we talked about a little earlier. Okay, last 3 slides here. So about infection location. Okay, when we look at infection by a pathogen, whether it be viral or bacterial, we could talk about a local infection, and it's pretty intuitive, right? An infection in one place, right? Local, it's local. It's localized to one place. Now, sometimes we talk about focal infections too, where the focal point is that local infection where you first had the infection, right? Think about maybe some dental work you have done, right? Or someone has done, and it does some damage and pokes into the gums there, and you have some bleeding, right? Which is not uncommon. So you might, if maybe the dental instruments or something like that are not clean, you could get an infection from that, right? And that would be a local infection perhaps. But if that bacterium, let's say, gains access to the bloodstream and it travels throughout the system and causes infection in other places, we would say that that was a focal infection. At the point that it traveled to other places, we'd say you have now a systemic infection, one that is spread to multiple locations, okay? Or body systems, right? So it could go from digestive to, respiratory or something like that. All right, what are some blood-borne complications then when something does get into the blood? Well, we talk about different things getting into the blood and put emia at the end, indicating it's in the blood, right? So bacteremia, well, bacteria are in the blood. Toxemia, toxins get into the blood. Viremia, virus is in the blood. Now keep in mind, anything in the blood that is deemed as foreign by the human immune system may be responded to in much the same way. You might have a lot of inflammation, right? You could go into anaphylaxis perhaps, right? You could actually have this widespread immune response and you're in trouble from any one of these. But this is where we can talk about what we talked about again earlier, which was not all bacterial infections cause bacteria to get into the bloodstream. At which point you would say you have also a term called septicemia. So these are kind of one and the same here, okay? Bacteremia and septicemia. But you could have a very small microbial load, so very few bacteria in a local infection, but so many toxins are produced, exotoxins, right, are secreted. So many of those exotoxins are secreted that they get into the bloodstream, and your problem is not necessarily the number of bacteria. You're going to be reeling and having a major immune response to the toxins that got into the blood, perhaps. And you can die from that reaction, right? Enough about that. One more slide about the course of infection. So a primary infection would be an initial infection that's produced by a pathogen. Okay, this was the original problem, primary infection. A secondary infection would be an infection that develops after the primary infection, right? So this infection sat there, caused major issues maybe, and then developed into another infection. Now this could be as a result of our own intervention, okay? So give you an example. You could have a primary infection, let's make it a urinary tract infection. And that urinary tract infection is for sure caused by E. coli. We did the diagnosis, we figured out there's this gram-negative bacterium causes the UTI. So I put you on some nice antibiotics, right, to get rid of that E. coli infection. And you come back a week later, 2 weeks later, and now you've got another infection. You've got a yeast infection, perhaps. Okay? Well, what's happened there is, for most likely, the antibiotic knocked out your initial E. coli infection, causing the UTI, but it also probably did some harm to some of the normal flora that live in those mucous membranes, in those regions. Okay? And now, the nasty pathogens that typically would be outcompeted in these regions, like yeast, have a foothold, right? They're able to get a foothold and actually cause this secondary infection. All right, last and not least, certainly not least, nosocomial infections, sometimes called healthcare-associated infections. These infections are acquired in a hospital or other healthcare facility, doctor's office, something like that, walk-ins. And this infection is unrelated to the reason for which the patient was initially admitted. So somebody goes in, they have maybe a minor issue, and they're sitting in the waiting room, and it's kind of scary nowadays. We're thinking about these things, right? Let's say you have an issue. I'll give you a personal example. My dad recently had some pretty serious surgeries, for real, and surgeries on his legs because he had poor blood flow, and he actually lost a toe in the process because his blood flow was so poor that they actually had to amputate a toe. Now he's good now. The pain has subsided from the issues he had, so I'm so grateful that he's well now. But he hasn't been to a place to get the proper orthotics to put in his shoe, and it was the big toe that he had taken off, so his foot's sliding around in his shoes, and he really needs some prosthetics, or some kind of foam or something to put into a special kind of insert into his shoe so that he can get around a little better. But he's wary of going to a doctor's office or just in public right now, right? We're worried about someone. He's 75, he's well, but he could be in a high mortality group, right? Being that age, and the fact that he has some vascular issues put him at high risk for COVID-19. So, he's worried about catching something like this. Nosocomial infections are no joke. All right, this is a little bit longer one, guys, but hopefully it'll help you, and you won't have to look up so many of these getting ready for that last exam. All right.